Fine. So this, if we can turn this one off now. Wonderful. Good. Okay, how about now? Good, excellent, thank you. It is a pleasure to be here because it's such a great workshop. It's such a nice school. I know of it, and I was hoping that I could be here previous years, but then of course COVID hit. So I'm very happy that this is happening in person, live here in Venice, no less. Thank you for the invitation, and hopefully it's going to be a nice workshop. I like the concept of merging nano and quantum, and I'll try to do a bit of that to show what, from materials side, how we need better materials and how we need better processing of these materials so that we can do something interesting for the quantum side, as long as we're not working with atoms. Of course, even that community, the atomic community, is now coming back and realizing, okay, we need good fabrication, we need good materials to control the atoms and the ions. And so there's a lot of crosstalk, which is great. The topic is shedding light on spins. Obviously, I'll be a bit of a pun. I'll be talking about optically active systems in solid state, in materials, and with a particular focus, given how broad their applications can be, the focus will be on quantum networks, or what we can achieve in that direction. But given that this is more of a school, I picked up some, I dug out some old slides just to give a sense of why we're motivated by this, why this is interesting, why would you want to build a quantum network or work on optically active systems. So I like this particular slide, so hopefully you'll appreciate it too. When we talk about creating correlations, I don't mean just about physically just two things, right? We immediately, the first slide goes to, here are the qubits and we'd like to link them. But take a step back and say, if you want to create anything correlated, such as matter, for example, you need proximity. So that word shows up quite frequently as a necessity, that's underappreciated necessity, that to get two things to interact with each other, you need proximity. You need to bring two things closer together. There's the length scale associated with the type of interaction they might have. And at the end of that interaction, depending on the exact nature of that interaction, their internal degrees of freedom might end up being correlated. It's not guaranteed, but this is the only way we know how to do it, right? So think of any interaction that doesn't require proximity at all. And that's not easy to find. So proximity is actually one of the fundamental key elements, requirements to actually bring things together. One example that I'm aware of, and of course there could be more, but one example that I know of that's practical and feasible for us is if those two entities, the two red blobs, as a physicist, these are simple toy models to work with, the two red blobs actually exchange energy directly with each other, so like through radiation. So if we actually have optics between these two red blobs, then we might be able to, again, not guaranteed, but we might be able to create correlations between these two red blobs, right? So then the question of proximity is no longer there. As long as I can pass the energy from one point to the other, the two red balls can be separated all of a sudden. So that's a good thing, right? And then if you put these two things, now in the context of nano, if you put these two red balls in some sort of a large cavity of some sort that defines an optical mode, a radiation mode, then what matters isn't the distance between these two red blobs. What matters is how well they couple to that common mode. And that's the principle of coupling through light in most systems, through a common mode. Quantum physics gives us one more element that makes it interesting and useful. And that is the concept of, for example, quantum erasure. And what it tells you is that these two red balls, as long as they have the ability to radiate, to pass on their internal degrees of freedom, information about their internal degrees of freedom to elsewhere, then instead of sending this message back and forth between the two, they can send it to a third party. And if the third party does a quantum measurement in the right way, this can induce correlations or interaction, effectively having done interactions between those two red balls. So you can see, and this means that the two red balls no longer even need line of sight. They don't even need to know of each other as long as there's a third party that does the right thing. Okay, I'll keep that in those technical terms of doing the right thing as a quantum erasure. So this all of a sudden means that if I have not two, but many of these red balls spread around, and if I want to create pairwise correlations, all I need is not direct line of sight between each other, a huge network that links them all together, but more like a puppet master that governs these pairwise, chooses these pairwise correlations, and simply pulls the strings to create those large correlated state. So imagine if we have at some point in the future, if we have the capability of creating hundreds or thousands of these red blobs and create engineered correlations between them, you're now talking you're going in the direction of correlated matter that is not linked to spatial locations. The proximity is removed. Now you have a spatially independent correlated state that's emerging from the system. So it's very interesting from a very, very different angle, very different reason why we usually get funded for this work. And the reason why we usually get funded is to actually create something simpler, and that's it's called a quantum network. And the idea is to get these red blobs, now they're not red anymore, get these red blobs, which are now quantum nodes, to actually carry or distribute entanglement or distribute quantum correlations between each other, so that information can be passed from one side to the other and distributed more importantly. A typical requirement, if people have looked into this quite rigorously, come up with essentially 3 key ingredients. Whatever your physical system of choice is, there are effectively 3 key ingredients that you need to provide in your system so that you have even a chance of doing something like a quantum network with extended number of nodes. The first one is the communication, this radiation channel that I was talking about. So, or what we call flying qubits. Think the information, quantum information, needs to go from A to B and stored. It needs to be distributed so that the correlations extend throughout this network. The second part is the processor qubits. This is some call it broker qubits. This is the qubit that actually has the ability to store quantum information and process it and pass it on. So this qubit needs to have strong interaction with light itself, the flying qubits. And then the last part is, it turns out that it is actually quite necessary. You cannot just do everything with processor qubits. You also need memory, local memory. So you can do some processing, do some calculation if you wanted to, or create a state, and you need to store that state until something else happens. That's part of the concatenation in any processing system. So you need to dump it to a local memory or a local register, and then when needed, you pull it back out. So this means that the processor qubit now also, in addition to talking to flying qubits efficiently in a quantum correlated manner, needs to talk to these local registers in terms of exchanging the information, storing it there, and then pulling it back out again. And the requirement for the flying qubits then is that they are not lossy. We can trust them. The processor qubit should be high fidelity and fast in terms of operations. And the local register should have very long storage time so that we can actually trust the system and we can retrieve it back out again. You can name your choice of physical systems that go into these 3 categories. There are, dime a dozen, but typically it ends up being some sort of photonic state on the flying qubit side. We don't have better flying qubits. It's difficult to shuffle matter around efficiently. So photons do a good job at the speed of light. The spin is usually a good metric for us to work with. Its performance is good, and I'll argue that even trapped ions or atoms, at the end of the day, you are looking at their spin states, spin-defined states. So spin is a generic term here. That's not just a single electron or a hole or something. And nuclear spins there are other examples to this. It could be other ionic species nearby or something. There are other ways you can realize the cluster, memory registers. But nuclear spins, as soon as you have a spin in a solid state system, ends up being a good, readily available, in most cases, unnecessarily available resource for you to play with. So they're around, they're hard to get away from. So as long as they're spin active, nuclei can be well isolated from the rest of the world, which means the challenge now is to find systems where the spin talks to photons very efficiently. So these are spin photon quantum interfaces that we're interested in. And at the same time, find nearby nuclear spins, for example, that efficiently talk to that electron spin, but do not efficiently talk to the rest of the universe. That's also a strong restriction, right? And also we want to be able to turn that interaction between spin and nuclear spins, electron spin and nuclear spins, off and on whenever we want. It's a big demand. So in this field, basically, the spin photon interfaces, looking for spin photon interfaces, a bit of a spectroscopy background, spectroscopy survey, if you will. The whole community goes out, looks for physical systems that could replicate what the conditions or satisfy the conditions that I just laid out. Ultimately, whoever you talk to, there are 3 ingredients on the way to, let's say, building up that physical system to make it competitive. The first part is you have to work on the stationary qubit side. So there's a lot of work that goes on to make, for example, the electronic spins or the local registers, the nuclear spins, efficient, high fidelity, controllable, and all that. There's also the flying qubit side. You'll see a lot of members of the community focusing on the photonic side of things, how to make the optical transitions better. The photons have to be identical. If two red blobs are sharing a radiation mode, it's a singular mode, so it has to be only one well-defined profile for the photons that are exchanged. So you need to fight noise and fluctuation in the environment issues. And then the third, slightly less appreciated effort that is actually critical is once you have this node, these two nodes, how do you connect the two together? That's slightly underappreciated in some cases, because that's seen somewhat as engineering or perhaps not the quantum science of things. But that is critical. How do you actually take the photon from A to B? It is not trivial. And in most cases, we most of the time don't take it from A to B. So the challenge of delivering the flying qubits from A to B is actually worth the effort. So there's a lot of efforts going on both in free space, fibers, waveguides, nanostructures. So that side, at the moment, progress is limited by that side. So any work that comes that pushes us further in that direction gives us an advantage on how well we can build these systems. So we're now in the regime where all three are coming together. So this is a good time for solid state-based systems to see if they can actually deliver something. And the puppet master concept that I talked about actually is exactly that. So basically what happens is you take these two, so now I'm getting slightly more scientific, so I'm showing three-level systems. So the internal state, the internal degrees of freedom I'm talking about, for example, are the spin projections of a ground state, for example. And linked to that is optical photon generation, or that shows that they can generate a spin to photon correlated state. And then once you take the photon somewhere else, this is where you have a chance to then distribute this entanglement, pass it on to other elements, like another spin. So here what you're seeing is a beautiful, beautiful proposal from 1999. And basically the idea is that rather than the two red blobs, as you see, talking to each other to create entanglement through proximity or light exchange, they're passing on their light photons, or even the probability of emitting a photon in this particular case, through a beam splitter to a detection line. That beam splitter and detection line itself is what magically is called the quantum erasure part. All I'm trying to do is measure a photon and not know where it came from. That's it, right? So the classical world has no concept of this measurement. If I want to measure, if I need to measure something, I like to know what it is. Whereas in this picture, I would like to measure, I want to make sure that no one else measures it, the universe. I'm the only one that measures it, but I don't want to know what the answer is. It makes no sense, but this is part of quantum world. That's why it's hard to explain what's going on to the rest of the public. And because we use terms like this, I would like to measure it, but I don't want to know what it tells me. And that the magic element there, of course, is the beam splitter. So then once I see a photon at one of the outputs, if the photons, the channels, the paths, modes are identical, then I have no idea which of the two red blobs, which of the two physical systems emitted that one photon. That's where the ambiguity comes in. You create superposition states, and then through two systems, you create an entanglement between those two spins. That's the main concept of it. And I highlight this because this is one concept that has been a very simple concept, a very simple picture, just as you see, one effectively single beam splitter is the whole experiment, right? It's not, of course, it's a whole room, because to actually get that experiment to work, rather than theory people, the experiment people have to work in a full-blown lab. But the nice thing about it is that it's been realized, exactly the same concept has been realized in many physical systems, many physical realizations of that red blob. We have trapped ions, superconductors, superconducting qubits, semiconductor spins, diamond defects, and more are being added to the list. So this might be even dated now. It's from 2007. This plot nicely captures the fact that the community is very large and we're working towards similar goals. And it's a nice platform to test, to see where your physical system, your favorite qubit, for example, lands on this map of entanglement generation rate versus the fidelity of the quantum state you created between those two elements. The concept in all of these data points you see are reported. They have different styles in reporting, but that's fine. But some are corrected, some are not corrected. But at the end of the day, if you look at the x-axis, it spans 8 orders of magnitude. So it's, first of all, I want to say it's amazing that we can actually have very, very different physical systems do the same experiment and come up with a very wide range of operation. And the second thing I'll say is but negative, and that is none of that, nothing on that x-axis is technologically viable or relevant. So this is all of that, everything on that x-axis is slow. So if you think that you're fast at the right-hand side, you're very slow, right? So we're talking kilohertz rates of generating entanglement when classical communication is, we're at gigahertz now. And we're unhappy with gigahertz because our Wi-Fi doesn't work. And on the y-axis is the Bell state fidelity. There are slight variations to the exact way you can do the experiment. There's a 2-photon scheme and a single photon scheme. So this gives a bit of a compromise between rate versus fidelity. So you can imagine that there's a diagonal line going across. But the thing I'd like to highlight now to emphasize is the highest fidelity operation actually is a color center in diamond. That's the NV nitrogen vacancy center. And they're gaining momentum. So this is at the top left side. And then they're gaining momentum even further now. This is now in Hertz range they've reached. And the reason why fidelity, they're champions of the fidelity side of the story is because the spin state, the ground state spin is extremely good quality. Right? And that's not intuitive because we're talking about a physical solid state system, a defect inside a solid state system when you're competing against the ultimate trapped ions or neutral atoms. And that's why even the notion of artificial atom, as has been used in the previous decades, starts to fail now because it's not really artificial in that sense. It's actually pretty good. Yeah. The far end on the other side of the story, it's nice that this whole distribution is captured by solid state systems in the end. The atomic systems are stuck in the middle. Sorry. The far end is semiconductor quantum dots. These are number 9 there, and then I highlighted the last one as well. So 2 are actually solid state systems, again, semiconductor quantum dots. And there you wonder why are they winning on the rate side? Maybe not on the fidelity side, but why are they winning on the rate side? They don't win on the fidelity because spin is not that great, because every single electron that you're interested in does indeed talk to a nuclear register, except that there are 50,000 of them. So there's a lot of them, way more than we want. And that's a problem because it's hard to control all of those. But the win for quantum dots is the rate of photon generation. So again, the two ends kind of highlight the spin being very good, optics not so, and the other end being photons being very good, the spin not so. That's the two ends. So there's just a few very random select of things achieved using the photonic qualities, the superior photonic qualities of quantum dots. Chiral quantum photonics, photonic cluster state generation, single photon nonlinearities, the boson sampling, high efficiency multiphoton boson sampling. These are all works that relied heavily on the quality of the photons that come out, despite the spin part being problematic or challenging. And I'll highlight one particular work, and we'll hear more about this later today, even the further enhancements. And this is the fact that, even like an analog to the atomic systems where you have an open cavity, large, big cavity with an atom trapped in the middle of it. Imagine the same replicated with a semiconductor quantum dot, and the spin is confined within 2 mirrors. There's literally 2 mirrors. And it's fantastic work from Richard Warburton's group. Now they can claim end-to-end connectivity of 50%, if I'm not mistaken, Richard. So that is a big win. That's where we are right now. So again, the great thing is that a solid state system is able to achieve the largest end-to-end connectivity. That's fantastic. 2, that means 1 out of 2 photons is lost. So it again puts in perspective how important it is to work on that third segment, the communication channel, so that we actually have something efficient to work with. So what I'll do is so that's the quantum dot side. As I said, Richard will give a very nice talk on progress on the quantum dot side. What I want to talk about today is other systems. So one system in particular, and that is diamond, this one. So I did mention the nitrogen vacancy center in diamond and the semiconductor quantum dot. I want to go back to diamond and say, can we actually figure out a way so that we have better spin than quantum dots and better photons than NV? This may not necessarily be the ultimate, it's not the best of both worlds, right? I'm not saying I want the spin of the NV and the photons of the quantum dot. That's a big, big challenge. That's a big want, right? I would love to have that, but I don't think it's readily available. So I'm going for intermediate. I'm going for something reasonable for spin and something reasonable for photons to see if the compromise of the two could work. And there, of course, highlighted only a few competing, let's say, or running candidates for coming out with alternative systems. And if your favorite system is not there, this is really a subjective list for me. So don't be offended. Yours is at and more. That's where yours are. So that's fine. Okay, so when we look into color centers, again, given that it's a school, I'll bounce back and forth between very basic and not so basic. But so when we talk about color centers in diamond, of course, we talk about all the nice colors. That's where the name comes from. Colors in various gems or various diamonds. And of course, each of those colors that you see, this precious material, is not coming from the diamond itself. Diamond itself is actually absolutely transparent and boring. So when you actually grow pure, nice, clean diamond in the lab, this is what it looks like. It's hard to tell between glass and diamond. It's the impurities that give you that color, because the impurities within the band gap, the very wide band gap of diamond, interact with light. And that's what gives you the contrast. One of those, the most abundant, which turns out to be magically the one that works for quantum systems, is the nitrogen vacancy center. And that's where, in a pure, otherwise pure carbon lattice, you remove one atom, one carbon atom, you replace it with nitrogen, and remove a neighboring carbon atom and just leave it like that. And then on top of that, you add one more electron. So you can imagine why such a combination is abundant, because it's, you replace these two things, plus you add an extra electron, and it turns out to be the most abundant, energetically favored color center out there, mainly because of the abundance of nitrogen, of course. So based on the system, this nitrogen vacancy center, it's optically active, and it has a ground state that is the spin 1. So it gives you this option to work with a ground state that carries some information, that can store some information, and optical transitions that can translate that correlation to other physical systems. And it is the only system we have today that actually was able to realize the 3-node quantum network. This is by Delft results, by Randall Hansen's group, and it's the only one we have. There are multiple 2-node experiments, and this is actually the list that I showed before, but the only one where that could be extended to 3 nodes, miraculously, again, turns out to be the one that has the worst optical properties. So if your spin is good enough, this is already a key for you, right? If the spin is good enough, you could wait long enough, or you could sustain your operation such that you eventually can build up the 3-node network. It is difficult to push it much harder, mainly because, again, the optical emission part, despite the good spin, is only a small fraction. So now relate back to what I said before, with Richard's results, 50% of the photons make it from A to B. Here, only 4% even goes out. So it doesn't matter how well you try to improve it, there'll be a fundamental hard challenge from the beginning. So the idea is to look at other color centers to see if there is any that can offer better optical performance with hopefully matching the spin side of the story. So we need we need that. So one example that came out among many others that were studied, of course, hundreds and hundreds of color centers exist in diamond. One that came out that you should know about is the silicon vacancy center. So it's the same concept, except instead of a nitrogen, you replace it with a single silicon atom, and then you have the vacancy and you have the extra electron. So that somehow is a magical recipe of remove 2 atoms, add one alternative atom, and put an extra electron. That works well. And the optical transition now you're seeing at the lower right is actually fairly sharp compared to the NV center. And what it means is that a good portion of the emission, like 70, in some cases 80% of the emission, actually comes in the relevant 0 phonon line, the uninterrupted optical transition that doesn't involve phonons in the process. So that's good. So the energy levels, however, are slightly different than the nitrogen vacancy center. There's a ground and excited state, fine, but then various interactions split these states until, if you also include possibility of a hyperfine, the silicon has a nuclear spin or can have nuclear spin. So when you include all of that, it ends up being a bit of a mess. And then you need to do nice spectroscopy to figure out which state is what, and then optical transitions. And in the end, if you do it well, you can actually you can use the techniques developed previously, but employed by the Nitrogen Vacancy Center, the optical detected magnetic resonance, to actually address these electrons, the final ground state being electron spin up or down, and the nuclear spin associated with it being up or down. You see how I'm building up now the story of the processing qubit plus the ancilla nearby. There's a nearby nuclear spin that's coupled, and that becomes your two systems. As long as you have the optical transitions, that's your trio that we talked about. So here's an example of driving the electron and nuclear resonances by using ODMR, and it gives, you're able to see Rabi oscillations and all that. So it gives us access by using optics and microwave combination, just like the NV Center to a certain extent. And then this measurement happened. So this is what you're seeing now is temperature versus the quality of that electron spin, a T2 star, not decoupled, not corrected, but as is, the T2 star of the electron spin. So what it tells you is that, first of all, it's crap because it's around 100 nanoseconds. That's nowhere near what NV Center has. But also it has a very strong temperature dependence between 3.5 to 5.5 Kelvin, 2 degrees change. And you're saying a factor 2 change of the T2 star. So there's a very strong temperature dependence, and already tells you, okay, something is up with, obviously, with photons. So what's happening in the system, interestingly, is think of it as from now on, any group 4, I'll do a spoiler, any group 4 color center you hear about that's in this category, think of it as a single electron in a double potential well, okay? So that means you will have these orbital states split by the tunnel rate between them, effectively. And then what it gives you is, unfortunately, this phonon-assisted either spin flip or not even spin flip, but phase flipping or phase scrambling phononic transitions. So then the quality of your spin is now muddled by the fact that there's an orbital replica of the spin up and down that you have in the system. So that's bad. So there are 2 ways you can fix this. You need to remove the phonons, so they don't do that. Or you increase the energy level splitting so that you probe the larger frequencies required for the phonons, and that also dies off fairly quickly. So there are 2 approaches. One approach, as I said, is what I call the brute force approach. That's cool it down further by bigger. You're gonna need a bigger fridge. You put the things in and you cool it down to millikelvin, and then miraculously, because the phonon density is, or the phonon occupation is removed, the coherence improves dramatically. We go from nanoseconds, hundreds of nanoseconds, to milliseconds now, and this has been demonstrated. So Silicon Vacancy Center is actually competitive, is actually nice physical system all of a sudden, if you just go down a couple more degrees, a few more degrees. There's another way, of course, of increasing that orbital splitting, and that's by, for example, you can use strain, or you can make, that's where the fabrication of new devices comes in. You don't have to cool down to millikelvin, but you do have to work harder on your actual devices. So I'll highlight these 3 papers as I think landmark papers in this field that said high silicon vacancy is no longer just a candidate, it is now a candidate for quantum networks, and the US is putting significant funding towards building quantum networks, mainly led by Harvard, essentially. But these are the 3 papers that showed, yep, it is possible, it is competitive, and it will beat the Nitrogen Vacancy Center. That's the claim. So what do I do? At that point, then I say, well, okay, let's look for other things. Why not? So, because there's always something better that you could go. And if you look, there's the carbon on that column for the periodic table. Right underneath is the Silicon Vacancy Center, but there are other ones. There's germanium, there's tin, there's lead, and then there's, does anyone know that one? UUQ? It's radioactive, so I don't think I'm going to touch that. But technically, it goes down the list, and you could explore what they do. And it's the first time, actually, that we figured out in this random search, needle in a haystack approach, random search for color centers in diamond, that we found a family that behaves exactly the same way. They all look alike. The only thing that changes are their specific optical transitions or splittings or something, but they're exactly the same picture of this double well potential with a single electron. So that's the Silicon Vacancy Center. Germanium Vacancy Center, exactly very similar, but slightly shifted. Tin Vacancy Center does something similar. And then the difference between them is, as you go down the periodic table, their ground state splitting increases dramatically. So silicon is 50 gigahertz or so. Tin is already at 800 gigahertz, and the excited state splitting is terahertz, 3 terahertz or so. So that means you should be able to actually operate, do exactly the same measurements with more and more elevated temperatures per color center that you pick as you go down on that list. So this is silicon vacancy center and this temperature versus ground state splitting. And the color code refers to the phonon limited coherence time you expect in these systems. The silicon vacancy center is at that terrible crap nanoseconds at 4K. But then if you, it's about 100 nanoseconds, and if you cool down to the dilution fridge temperatures, all of a sudden it becomes milliseconds, many tens of milliseconds quality, right? That's the concept. So if I now go down on this list, this is where the other systems will actually end up being. And this is the one tin at 1.7K. It's supposed to provide, again, many milliseconds, many tens of milliseconds coherence time without requiring a dilution fridge in the lab. Still requires 1.7. But of course, if we can get to lead, then this would be comfortable at 10K. So this, even a flow Christ, that would be perfectly fine for this experiment. Just for the note, you will hear a lot of people say room temperature operation of this and that. If you're working on quantum networks where you need the photon to be correlated to the spin, there is no room temperature operation. There's no physical system that operates at room temperature. NV center is cooled down, HPN is cooled down, quantum dots are cooled down, everything is cooled down. Just so you know. All right, so let's look at the tin vacancy center. And this is now, it's an alternative to the SIV, which was an alternative to the NV. So this is how science progresses. We keep looking for new things. It has very similar profile as I mentioned. The ground state, however, now is split at 850 gigahertz. That's what I was talking about in terms of the more you can split it instead of 50, if you can get to much larger splittings, the phonons you need will be of that frequency, and it's hard to find those. So 850 gigahertz is actually quite impressive, to the point where the optical transitions, the four main peaks you should be seeing, two of them you don't even see because you never get to those states. The decay is so fast. And it turns out that you can do everything that we can do with other systems, including quantum dots, you can do with the system as well. You can create a small 3-level system in a subset, and you can do all optical drive of the spin using detuned lasers, Raman lasers. These are all borrowed from atomic physics experiments, and you can see Rabi oscillations and Ramsey and whatnot. So this is an example of Ramsey. And what is nice is that the T2 star of the tin vacancy center at 1.7K is the same as what you get for the NV center. Okay, at room temperature, but still what you get for the NV center, because the noise, the deciding noise noisy environment is carbon-13 at the end of the day. So this is it's nice to see that the tin vacancy also performs in a similar way. And if you do dynamic decoupling protocols, then you can extend it to, at the moment, to microseconds, hundreds of microseconds, and it's limited by availability of an M2 laser. That's it really brings it down to the very basic thing you need in the lab is high power laser, and it's work in progress. So, of course, these are systems isolated. They're in bulk diamond. They're not necessarily integrated into something. And whereas many other physical systems like quantum dots have already been integrated into very nice nanostructured devices. But there is hope for diamond as well. This is work together with Dirk Englund that we do. Basically, these are waveguides, and diamond is not the greatest material to process. It usually cuts everything else. So it's difficult to actually cut diamond in the exact shape that you want. So it's always a challenge. But basically, the idea is then to create this hybrid structure where the diamond that hosts your quantum system that you're interested in is a small portion of an otherwise well-developed system like aluminum nitride or silicon nitride photonic waveguides. So the idea is that you would make these, you fabricate these chiplets, these chiplets, and you break them off, and then you place them at the dedicated location. And they have done parts of this to see how far they can push. So it is actually technically possible to create a large chip of many of these chiplets incorporated in the system. So the question is, how well do these systems perform in such an environment? You always have degradation of the quality of the spin and photons when you put color centers in close proximity to surfaces. That has been a big challenge, and that's where material science comes in as well. Finding the right color center, but also working on how to manage surfaces is a key question now in this quantum work. So we took one of these chiplets, we placed it so it's hanging off the edge of a sample holder. we approach with a fiber tip to collect from the end of the waveguide to do spectroscopy on the quality of the photons. I'll pass quickly on this, but you can do optical Rabi, optical Ramsey, Haneko, and you can see that we're not exactly at the fundamental limit, but it's not too far off. So we're about a factor 2 off from where it needs to be. And the two things that are relevant for the quality of the photons, in addition to the collection rate, the photon generation rate, is the photon purity. How pure is, when I say single photon, is it really single, or is there multiples? So the photon purity is actually quite good in these systems, coupling out from a waveguide. The visibility for how indistinguishable they are, that's that magic beam splitter performance that I will need later on. This is 73%. I think it's a good starting point to improve further later on. So basically this is, so I'm proposing tin vacancy center as the next thing. That's interesting to study and it has some work to be done, but it's coming along. And the fact that diamond itself is providing this color center is impressive. So with the remaining 2 minutes or so, I suppose, given that this is a school, I want to reflect on two elements. The first two topics. One is quantum networks, and it's worth talking about these things now that we're getting close to actually realizing it's not just a motivational thing. What is the killer app? I don't think this is known. I don't think, and we have disagreements on what we think is the killer app. So I think it would be good to talk over lunch or something, or over beer. It'd be good to talk about these things. And I claim that the most interesting application of quantum networks, if we can build it properly, is going to be sensing. Distributed sensing is probably one of the interesting things that has some analogy to IoT type current applications. The second thing is pick your battle. So you cannot get long distance quantum networks with many number of nodes and node content, many ancilla qubits plus a processor qubit, 20 of these together, million of those distributed across continents. This is a big ask. So pick your battle. Do you want a small cluster that interacts very efficiently and does a processing, does a particular task for you? Or do you want to actually communicate over long distances where each node is not so demanding? And then the concept of so you could say after these two, you could say, why the hell are you doing it then? If this is so difficult, then maybe you don't know what it's good for. Actually, I also claim that it's going to be needed by every physical system if you're building a quantum computing platform. At some point, you run out of chip. At some point, you need to interconnect. And this is verified, and I can say this, it's verified by superconducting people. So as long as they say that they will need interconnects, I'm happy. Then it's worth working on this system. And we need a lot of non-quantum expertise. So we need a lot of nano, we need a lot of fabrication, we need a lot of material science to support, because as you've seen from the beginning of the talk, the quantum physicist approach is the red blobs. So we need the real world to come in and fix it for us. So that's why these kind of meetings are always important. And as a final thing, a moment to reflect, because I talked about optically active defects, I did highlight the many different physical systems being pursued. It's, of course, we still don't have the one, right? There's no one system that we say, okay, that's the one that will deliver definitely the quantum networks. I'm not selling tin vacancy for that, I'm hoping, but we still don't have the one. And I highlighted not the one, but I highlighted, underlined, have. And that's a problem because so far, all of these, we have them, we don't make them. The advantage of superconducting systems is that they make them with their faults and irregularities and all that, but it's limited by what you can do. Whereas in our cases, when I talk about a color center in diamond, this is what I have rather than something I make in the lab, right? So there's that element to think about. Is there a way to turn that have into a make so that we can actually see if we can go beyond what nature gives us? And exploring alternatives, this is another concept, is a good and a bad idea. So it's good because we can look for things that fit better, but it's also bad because we keep searching for the next thing. It's what I've done. As soon as we saw the silicon vacancy is competitive, I moved to something else. That's not good because we need to focus on the one thing and deliver it just like trapped ions have done, for example. So there's something to learn there from that perspective. And it's always the case that the material maturity takes time. It's the same diamond, it's the same defect that was studied for a decade or more, 2 decades. Same thing with semiconductor quantum dots. They've been studied for 3 decades, but it takes time for the material quality to deliver you that cleanness that gives you the physics that you're interested in. And with that, I will finish off and say, thank you very much.
hope this will not give interferences. This looks fine. Well, thanks again for a wonderful talk. So now we have questions. Please go ahead. Don't be shy. I will take them from the back onwards. Yeah.
Hi, thanks for the talk. My question is regarding like the entanglement generation rate. You said that those data were from 2007. There is no increase in entanglement generation rate?
There is, that figure was made in 2017. Since then, I think there's some improvement on the NV side, and there's some on trapped ions in cavities. So they may not be included in that one. So I need to check the improvement. There's also, it's important that these are measurement-based ones. So take the photons from two separate things, but then you have to make a measurement on third party. There's fantastic work from Andreas Wohlraff where the photons, or microwave photons are going from A to B in this crazy experiment where there's the Dilfridge here, and a sideways Dilfridge effectively linking the two. You know, it's not really a quantum network, fine. And then basically there's a microwave line, cold microwave line that goes through, and their efficiency is off the charts, right? That's at still on that scale, but it's at the far end point. So they do get that direct link because it's not lossy. But we were excluding that because it's direct one-to-one, because I can't really do too many of those. Okay. Right, okay, I'll repeat the question.
So let's work our way further forward. There were more questions in the back. Well, they have become shy, so then it's all you.
Yeah, thank you for your talk. I have a very simple question. So you said that lead vacancies would have longer coherence times, even at higher temperatures. So why did you not choose those now to study and stick with tin vacancies?
Yes, thank you. It's an obvious question. The question is, well, if you claim that going down the periodic table gives you longer coherence, why don't you just go to lead or UUQ technically? The reason is we did try to go directly to lead. And of course, you should never skip steps. You should go one by one. This is how science works. The reason why we didn't work with lead is because lead is actually too fat. So it actually, when it goes into the material, it destroys it more than it creates the defects themselves. So what you want is you want your atom to go in, breaking bonds into diamond, and then sit somewhere when it runs out of kinetic energy. And then you want all that damage to disappear, right? So we do that by annealing. So we heat up the material, the vacancies move around. One vacancy finds the atom because it's energetically favorable, and that's your vacancy, you got it. But the rest, you want them to go away to the surface. With lead, the damage is too big that they don't go away, they pair up and then they linger around. And the quality is, you can actually physically see where if you have done lead irradiation, it looks ugly. I mean, you can physically see that it's bad. So until we fix that problem, which is not quantum, but we need to fix it, then tin is the favorite one. That's one material science perspective. There's one other element to it to highlight. As we split the energy levels, the optical transitions still work, but there is absolutely no chance for microwave at that point. The one-to-one direct magnetic connection is lost completely. So even if you could deliver high magnetic field, high frequency microwaves, the transition disappears. So you have to rely on orbitals. So optics is your only way. That's the reason we settled.
Yeah, many thanks. So I want to have a follow-up on the entanglement rate question. So you said that you need the right amount of spin coherence, if I interpret you correctly. So I think we all want at the end megahertz or gigahertz entanglement rates. So what is your take on how much spin coherence do you need actually at this point? Because I suspect that you can get along with pretty mediocre coherence times then. So is there a figure of merit?
It's a very good question, actually. That takes me back to that slide. There is no direct figure of merit, but basically I'll give you two very informal, rough figures of merit. One, T2 and T2 star. Those are critical things, obviously. But you would intuitively say, well, T2 is what matters, because that's when you're holding on to your electron spin coherence while the photon is going somewhere, right? It goes at the speed of light, divided by n, whatever n is in that medium, but it still takes a long time to get if we're talking about distributed networks, right? So you still have to make sure that the electron keeps its coherence in the process. We do this by dynamic decoupling techniques. So we can actually, with NV does a fantastic job at this. So you can store it up to a second almost, right? So that's great, but it's about a second. So how far a photon goes is determined by that time scale. That's T2. So what you need for electron spin coherence that can be decoupled, the protected one, that is dictated by what your architecture looks like, how far your things are spread out, the nodes are spread out. But there's another fundamental one, that's the T2 star. You can't get away from T2 star because in the beginning, when we're generating the photon that is correlated with the spin, there is no dynamic decoupling you could do. You wait for the duration of photon generation. In that period, any decoherence you have in the ground state is imprinted on the quality of your spin photon entanglement. So it doesn't matter how well you can protect later on. There's a very nice paper by Ronald quite recently on the archive to show what the fundamental limits of NV-based quantum networks are. And they highlighted there as well. Ultimately, your T2 star matters. So you have to make sure your T2 star is good. In quantum dots, semiconductor quantum dots, they have the best performance for photons. That's why that's the axis without cavity. So the last two are there as best performing systems without any cavities. And then when you incorporate the very nice cavity results, the very successful cavity results, that's going to be off the charts over there. That's going to be many, many megahertz, many tens of megahertz. So it's going to be the most competitive system possible. But the spin coherence, if you don't do anything, is around 1 to 2 nanoseconds. The photon is about a nanosecond, roughly, or it's a bit less. So you're starting with a big hit already. So you need to improve the T2 star so that it's 1% limit or 0.5% limit or 0.1% limit. So the T2 star needs to be long. And we figured out in the community, we figured out a way to do this so that we can reach what, 10 nanoseconds or 100 nanoseconds now. So that becomes now possible. So that would be the second number you have to care about. The time it takes to generate a photon versus your T2 star.
Okay, so there's one problem I have. All the questions have been from this side. Can I encourage someone on the other side to ask a question?
Or if you have a question, please move to that side to fix the problem.
In the meantime, I will.
We do have one question there.
On this side.
Yeah, I think that's fine.
Thank you. I might have missed it, but what are the typical lifetimes for the 10 vacancies for the excited state?
There are a few nanoseconds,
Okay.
3 to 7, 3 to 5 of that order. And it does depend on the structure that they're part of. In bulk, they're a bit around 4 to 5 nanoseconds.
Okay, and the typical gate operation times, for example, for spin rotations, or I guess, do you use microwaves or do you do
We
that
use all optics.
optically?
All optics for optical transitions. It depends on the power of your laser and how well you can keep how good quality your laser is in the end. But we can do it on the order of a nanosecond. You can do pulse like picoseconds, but we like to do this EOM based controlled experiments. They take about a nanosecond or so. Okay. For the optical transitions. It's longer for the spin. Many nanoseconds.
So did I get this right that you said there have been lots of experiments with 2 nodes and then it was a big jump to 3 nodes?
Yeah.
And then of course this asks for the obvious question, what about 4, 5, 6? How much does one actually need realistically?
To do anything interesting? A lot. And 3 digits is roughly what you need. But you can do certain things with, again, if your application is, for example, sensing, then 2 will work fine. The concept is no longer limited to the number of nodes. To make it interesting enough, if you want to talk about a distributed processing scheme, then you need the same number of qubits that you would need for a computer as well. So something on the order of 100 to 500 would be already quite relevant. It would be in the interesting regime. But yeah, 4 is difficult, and this is why Delft is also working very hard on other systems, because ultimately there's a limit.
Mm-hmm. So are there further questions?